All right, so today we're starting chapter 9, section 9.1. We're looking at modeling with differential equations. Now, chapter 9 deals with the topic of differential equations, and really it's just a very, very brief introduction to the introduction to differential equations. We have a full intro to differential equations course that we offer. I teach that one. I have a full playlist. It's Math 420 on this YouTube channel for that class. And I cover a lot of the same stuff that we cover in chapter 9 at the beginning of that class. The goal here is to just kind of dip into the topic of differential equations and show how some of the work that we have done up until this point can be used in solving them and kind of just generally dealing with them. Okay, but this is probably going to be your first exposure to differential equations, so we need to start from the very beginning. What is a differential equation? Oftentimes we use DE as for short, as an abbreviation for that. So basically, a differential equation is an equation that contains the derivatives of one or more unknown functions with respect to one or more variables. Now, for us, this is a very general equation or definition because it includes something that we're not even going to touch on in this chapter, something called partial differential equations, which are differential equations that involve multivariable functions. We can't even begin to talk about that until we've had Calculus 3, where we talk about multivariable functions. So for us, really this definition can be a little bit more refined, and we can say that it's a differential equation containing derivatives of one or more unknown functions with respect to one variable. That's the kind of things that we're looking at here. The order of a DE, or a differential equation, is the highest derivative that appears in the equation. So here's a couple of examples of differential equations. Here is a first order differential equation, x squared dy dx minus xy equals cosine of x. So notice here, we're having x's and y's appearing in this equation, but because there is a dy dx showing up, that's implying that y is actually a function of x. They're not two unrelated variables that are showing up here. The y is actually a function of x. So we think of that y as a function the entire time, while we're thinking of x as just an independent variable. It's a first order DE because the highest order derivative of my y function that shows up in here is dy dx. That's the first derivative of y. That's where we get first order from. Here's an example of a third order differential equation. The y triple prime plus 4xy prime equals the natural log of y. Okay, so this is a differential equation because I'm getting derivatives of y showing up in an equation that relates it to the function y and other functions of x throughout here. And it's third order because the highest derivative I'm seeing here is a third derivative. I don't need a second or first derivative to show up in here anywhere. It's not a problem that there's no y double prime anywhere. Just the fact that there's a y triple prime and that's the highest derivative is what makes that a third order DE. Okay, finally, a solution to a differential equation is any function that satisfies the equation. So in other words, if I look at this thing right here, I'm trying to find a function y such that if I take its third derivative and its first derivative times 4x and then subtract those, I get a function that's the same thing as the natural log of my original function. That's kind of a long way of saying that. But basically, when you're solving these DEs, it's different from solving an equation in algebra. Because when you solve an algebraic equation, your solutions look like numbers, either real or complex numbers. Whereas here, our solutions look like entire functions. Okay? Generally speaking, as we're going to see a little bit later, a differential equation will typically have infinitely many solutions, but usually those solutions all take a very specific form and we can categorize them. So we'll talk about that in a little bit. But before we go any further with the actual hands-on stuff with differential equations, I want to talk about this thing, the modeling thing. Why do we care about differential equations at all? What's their relevance? Well, it turns out differential equations are arguably one of the most important objects in mathematics, period. That's going to get some flack from different people because that's kind of a subjective statement. But the reason I say that is because differential equations show up in pretty much every single branch of the sciences, like literally all of them. And it's because what they do is they relate a function, which we know shows up all over the place, to the rate of change in that function with respect to its independent variable. So I'm going to show you a few examples of mathematical models, which are equations that are designed to describe a physical or otherwise phenomenon. And the one we're going to start with is the idea of population growth. So this is a very straightforward example, kind of showing where a differential equation would come from. So what we're going to do is consider that we have a population that's capable of reproducing. It can be humans, some type of animal, bacteria, just something that's capable of growing its own population through reproduction. If you think about it for a second, the larger that population size is, the more candidates there will be for reproduction. What that means is you have more reproducing pairs of organisms, which also implies that the rate of reproduction will grow larger as the population grows larger. So what we have is a direct relationship between the size of a population and its rate of growth. But a rate is what we use derivatives to represent. So right away, we have a relationship between a function and its derivative through this description right here. So what we're going to do is we're going to let P represent population size, and it's a function of T, because the population of this group or community or whatever it is will change over time. It'll grow, it'll shrink, it's potentially going to change over time. That's what makes it a function of T. The rate of change in the size of this population is dp dt. So we're kind of assuming here that the population is growing, okay? How do we come up with a differential equation or a mathematical model describing this little paragraph right here? Well, we're saying that the rate of change in our population will increase as the population itself increases. In one instance in which that happens is when two variables are directly proportional to each other. So to say that one variable is proportional to another is to say that it's equal as a variable to some constant times the other variable. Here, what that would imply is that dp dt, our rate of change in population, is equal to some constant times p, the size of the population. So as p gets bigger, so does dp dt, as long as that k is positive, which you notice I'm kind of assuming here. Okay? Now, how do we find a solution to this? So in this case, p is the function, and the goal with a model like this is to come up with a function that represents the population of this community at a given time. That allows us to make predictions about population size in the future, which is a useful thing to do. We're not going to talk in this section about how to solve this just by looking at it, but we are going to talk about how to verify if something is a solution. So right here, I give you not just one solution, but an entire family of solutions. P equals CE to the KT. And where is this coming from? Well, if you're kind of thinking about it just in like a guess and check sort of way, I'm looking for a function that is almost equal to its derivative. It's just a constant times itself when I take the derivative. If I think about what kind of functions do that, what kind of functions are either equal to their own derivative or just a constant times the or is the derivative equal to a constant times the original function? Exponential functions do that. You can verify if I were to take the derivative of this, CE to the KT, I would get CE to the KT times another K because the chain rule would spit a K out there. But that's just K times the original function, which is exactly what this is saying. So this is a solution to this differential equation, but I'm using a capital C here. That C can be any real number that I want. It could actually even be 0, and it would still work. So this represents an infinite family of solutions depending on all the different possible choices of C. Okay. Now, if we wanted to, we could graph some representative solutions, meaning we could choose a few different values for C and graph the curves that we get from those functions. And here's what several of those would look like, roughly speaking. These are all exponential functions. We know that exponential functions tend to look like this. They're increasing as we go from left to right, unless that C is a negative number, in which case you get a reflection of these things across the t-axis. So it's some of those will go down like that. So this is giving us a sense of what the solutions, many of the solutions to this DE might look like. Now what we want to do is single out the solutions that are relevant to the discussion that we're having. So first of all, we're talking about population growth here. Populations can't be negative. So none of these curves down here make sense in context. Even though they are solutions to the differential equation, when we think about what the differential equation represents, you cannot have negative populations. So none of these make any sense. Furthermore, even if all of these solution curves up here are kind of fitting for our description, we don't really want to have negative values for time either. So it doesn't make a whole lot of sense to include all of these curves up here, because when t is negative, that doesn't really make a whole lot of sense. So we can trim things down a little bit by only looking at the parts of those solution curves that satisfy kind of the context of the problem we're working with. Now, we're having a discussion about population growth, and it may seem that we have solved the problem. We found a model for population growth. We found functions that model population growth. That sounds great and everything. But there's an issue, a pretty glaring one, with these solutions. One thing that we know about exponential functions is that they tend to grow very, very fast. Faster and faster the further time progresses in this case. And they don't ever level out. They just kind of shoot off to infinity. So is that what we actually observe in nature? Do we see populations skyrocketing to infinity, growing ever faster as time progresses? And the answer is no, that doesn't actually happen in reality. So what's wrong with our model? Well, we were taking too simplistic of an approach. Even though it does seem reasonable to say that a population will grow at a rate proportional to its size, that's only taking the number of reproductive pairs of organisms into account there. It's not taking into account other things that influence population. So first of all, it didn't take into consideration the fact that some of those members of the population will die. So there's something that's negatively affecting the population size, not just positively affecting it. In addition to that, and kind of more important really, is that populations of organisms, whatever they happen to be, exist within an ecosystem or an environment. And that ecosystem or environment has what's called a carrying capacity. So I'm talking about that right here. Carrying capacity. Basically what that represents is a maximum number of members of that population that can exist in that environment before it's no longer able to sustain that population. So if you think about like I don't know, maybe like a group of zebras or something in the savannah. They can reproduce, their population can grow, but the more members there are in that population, the more resources they need to survive. Things like water, food, etc. Right? If your population grows too big, you're going to exhaust those resources faster than you can replenish them, and that's going to be a death sentence for your population. So populations tend to level out over time because they can't exceed this carrying capacity without catastrophic consequences. How do we take this carrying capacity idea into account in our mathematical model? Well, we want to look at two conditions now that we want our population growth model to satisfy. First of all, we would like for our population growth to still be proportional, or at least close to proportional. That's an approximately symbol right there. Close to proportional to population size, as long as p is relatively small. So as long as we're not very close to our carrying capacity, we actually do want our population to grow at this kind of a rate. But as p gets closer and closer to that carrying capacity, we want this to level out. And in fact, if we ever exceed our carrying capacity, so if our population is ever greater than capital M, which is what we're using to denote our carrying capacity, we want our rate of growth to switch to being negative. In other words, we want a decrease in our population size to bring us down below that carrying capacity. So there are different ways of modeling this. There's not just one specific way to do it, but here's one way. If I set up this differential equation, dp dt, the rate of population growth, is equal to c, where c is some positive constant, times p times m minus p in parentheses. So let's think about this for a second, okay? First of all, I can simplify what this looks like by factoring an m out of the parentheses here. If I factor an m out and multiply it to this constant c here, I'm just going to call the corresponding constant k. So k is equal to c times m. This will become a 1. This will become a p over m when I do that. Now, consider what happens when your population is very, very small relative to your carrying capacity. So specifically, I want to look at what happens to this term right here. If p is very, very small compared to m, then this fraction is going to be relatively close to 0. Small numerator, big denominator, which means 1 minus that is going to be pretty close to 1, which means kp times this is pretty close to kp. So when p is small, dp dt is pretty close to kp. That's the first condition that we wanted to satisfy. What happens if p exceeds m? So that's the second condition. Well, if p gets larger than your carrying capacity, then this fraction will have a larger numerator than its denominator, so it becomes greater than 1, which means 1 minus that is a negative number. And since k and p are both positive, multiplying it by a negative number would give me a negative value here, which is what we wanted. We wanted that dp dt to come out negative. So this model satisfies these criteria. It's not the only model that does, but it's an important one that does. And we call this the logistic differential equation. Oftentimes it's just called the logistic equation. And it's actually a much more reasonable model for population growth in most circumstances. Now, even though we're not going to be able to find any solutions to this yet, there is some interesting information that we can get out of this. First of all, suppose for a second that you start with a population of 0. Okay, think about what would happen at a population of 0. If your population is 0, you have no ability for population growth because there are no members capable of reproduction. So your population is going to stay at 0 the entire time. Okay, but now come up here and look at what p equals 0 implies about this differential equation. Well, if I have p equals 0, I can plug that in for the p's here, and this whole thing goes to 0. So I have dp dt equals 0. But if the derivative of a function is 0, that means the original function is just a constant. And we know exactly what constant it is, p equals 0, because we have a point on that curve. So that basically says that this model confirms our suspicions. If our population starts at 0 members, it will stay at 0 members. It will stay at that constant. Similarly, what happens if my population at time 0 is exactly equal to my carrying capacity? What if we start out at the carrying capacity? Well, I would plug an m in for p, and notice here I have p in my numerator. If I plug an m in for that, m over m is 1, 1 minus 1 is 0, this goes to 0. Same thing happens. dp dt is equal to 0, which means p is a constant function, and in this case, we know that it would be equal to the constant m. So what does that mean? That means that if your population is already at carrying capacity, it's going to stay at carrying capacity. And that kind of makes sense, at least as far as the model is concerned, because we saw that we get exponential growth or something close to exponential growth, if this is an approximation right here, when p is small. That's positive growth. We saw that if we exceed our carrying capacity, our population decreases. So if our population increases below the carrying capacity but decreases above it, it kind of makes sense that it would be 0 growth on the carrying capacity, which is kind of what we're seeing here. If our population stays at m, then we're not growing or shrinking. So when this happens in a differential equation, when you get constant solutions to a differential equation as opposed to more complicated looking functions, we call those equilibrium solutions. And here's a graph depicting some of those. So these colored curves here are different solutions to that logistic equation. Notice as time progresses, we have kind of an increasing rate of change in our population up to a point, but then we switch from being concave up to concave down. So that means we're still growing, but at a slowing rate as we approach this M, our carrying capacity. For the curves that start out above our carrying capacity, we see them decreasing towards the carrying capacity. So these curves kind of confirm what we suspected would happen with these logistic solutions to the logistic equation. Now notice it says equilibrium solutions. P equals M and P equals 0, these horizontal lines. They're horizontal lines because they're the graph of constant functions, which is what we had pointed out previously. So this is basically what we were talking about before. Equilibrium solutions are constant solutions to a differential equation. And differential equations can have those as well as non-constant solutions like we're seeing here, okay? You do a little bit more with that concept in a full differential equations class, but that's where we're going to leave that one for now. The only other mathematical model I want to talk about is the motion of a spring. And this one should ring a bell because we talked about this back in 6.4 when we did work problems. If you recall, we used something called Hooke's law, which says that if you have a spring and you have, you know what the length of that spring is before any force is applied to it. We were calling that the natural length of the spring back in chapter 6. But here we're going to be a little bit more specific. We're going to impose a coordinate system on our spring. So here's that spring when the mass has not really been applied there. And whatever its natural length is what we call the equilibrium position. We set that equal to 0 on this x-axis. We're going to orient this axis so that the positive direction is actually down, which means if you stretch the spring, its location is going to be denoted by like a positive value for x. Compressing the spring would give us negative values up here. Okay? Now, if you were to take a spring and suspend a weight from it or pull it down or, stretch it in some way, then the spring is going to exert a force in the opposite direction. And it's going to give you resistance. You know this just from, I'm sure all of you have pulled or, stretched a spring before. It exerts a force trying to restore itself to equilibrium. So if you're pulling in the positive direction, then that restoring force is going to act in the negative direction. And from Hooke's law, we know that the force exerted by that spring is a constant times x, its position, kx. But to indicate that it's pulling against the force that's stretching it, we need a negative here because that force would be applied in the negative direction if this is a positive, if it's being stretched like this. Okay? How can we express this idea, but instead using a differential equation? Well, we're talking about forces here. And Newton's second law, which we've already used in this class, states that the net force exerted on an object is equal to its mass times its acceleration, okay? But from Calculus 1, we know what the relationship between acceleration, velocity, and position are. And remember, this x here represents the position of that mass. So the acceleration of that mass on the end of the spring is equal to the second derivative of its position, x of t. We're thinking of this x as a function of time. It changes as we stretch, as time passes and we're stretching and compressing the spring. Okay, so that means that the force, the restoring force of the spring can now be represented in two different ways. M times the second derivative of x with respect to t, and negative kx according to Hooke's law. If I solve this for that derivative, I get that the second derivative of x with respect to t is equal to negative k over m times x. And this is a second order differential equation. This time x is not the independent variable, it's the function. T is the independent variable because the position of the spring will change over time. So whatever solution we get from this will look like a function x of t. Okay? All right. I'm going to end this video here, and we'll start doing some examples in the next video.